I'm running this selective amplifier at 10 megahertz to see what happens with time when it gets warmer. The power is very close to 1 watt. I have a 20 dB directional coupler. And the setup is as in previous videos. Look on the earlier ones in this series for nerds only. What I can see here is that the noise is increasing slowly. Starts at 1.9 something and it has gone up to 2.2. This table shows the noise increment here, the corresponding noise figure and the corresponding noise floor. So going from 1.9 up to 2.2, it is about half a dB. I will now switch the unit off. So after switching off, it's clear that it takes some time. Here I switch off, something cools very rapidly, and then it cools slowly over a long time. I think this is the output resistors. They get pretty hot, so they should give some noise. I have to arrange for cooling for them. And I switched it on again, and you can see that it's now racing pretty fast. So this is the rising temperature of something. I have glued the output resistors to the wall of the box at this place, and I put some black polyvinyl tape in order to be able to measure the temperature. It's now 26 degrees, well, 27, 26.4, well. And then the transistors are sitting here, and that temperature is also about 27 degrees. I have connected this noise head to the test system, and this is what I observe. The noise floor with a room temp 50 ohm object on the input, and it's calibrated to show almost zero, 1/100th of a dB error. And now I will switch on this amplifier. There is nothing on the input, it's an open cable here, but there is a 50 ohm dummy load on the feedback output, and I connect the test system to this output here. And while nothing was connected, the noise was a little bit lower, but now the impedance is not perfectly 50 ohms, but it's not too far away when there is no power on this unit. So I switch on the power like that. It's 19 volts. And then you can see the noise goes up significantly to about 1.7. 1.7. And I don't know if I can read it out here. Yes, 1.64. So the noise increase is a little bit lower than 1.64, means that the noise floor is a little bit better than minus 168 dBm per hertz. And there is no signal. Of course, there is no feedback. So I disconnect this resistor and connect power here. Sorry, feedback. like that. Then oscillations start and I get nearly 10 dBm. It says 9.9 at the moment. It changes probably a little bit with temperature. And the noise went up, and for some reason there was a phenomenon here for a while. That's typical for crystals, and whether that is in the test system or in the oscillator, I don't know. But there is a long time trend that the noise floor is increasing. So I will wait for a while. Now 10 minutes have elapsed and the noise I see is, I don't see it yet, but soon, 1.9, and it's still going up. This is the 1.9 line, which is being crossed. These peaks are from crystal noise, and I think it is the test system and not the oscillator. So 1.87, it is now degraded the noise above minus 168, and the temperature at the output resistors is about 40 degrees, and on the transistors about 62. And now I will wait for quite some more time to get the final temperature. Now the unit has been running for more than 1 hour, and it doesn't look so good anymore. The noise floor is 3.2 dB. That means we are at minus 164 dBm per hertz, roughly. But it's not stable. And the power is no more 1 watt. It is plus 29 dBm now. The temperature here is 73 degrees. That's on the transistors. And on the output resistors, well, it says 45 or 50 degrees. So it's pretty hot. I switch it off now. I have to move the scale. And we are here at about 0.15, and it is cooling rapidly first. That is probably the silicon, and I will wait for a while now. This is 10 minutes later. It's going down, and now it reached 0.04 dB, while it started here at 0.09. So it was about 0.1 dB. That is the contribution from the heat of the box. The temperature now is, what do we see? 35 degrees on the output resistors and 37 on the transistors. I have made a cooler now from copper sheet, about 3 millimeter thick, and I'm waiting for it to get fastened to the box. I have put epoxy resin to glue it to the box. It has been running now for a couple of hours, and when I look at the temperature, it's 32 degrees. So it's not so hot anymore. And this is what I see on the Linrad screen. 1.8 dB. So it's something like not so far from minus 168 dBm per hertz. The power output is 9.5 dBm here, means 29.5 dBm. So this is about minus 197 dBc per hertz. Now there are some problems with the evaluation system. You can see occasional occurrences of noise from the crystals. That's from the crystals on the test system. So to really know what's going on is a little bit difficult. As it turns out, crystal noise is generated in the selective amplifier and not in the test system. So I have to reduce the power on the crystals. Right now I have plus 15 dBm, and I will step it downwards in steps of 0.1 dB while looking at the screen of Linrad. So 0.1, 2, 3, 4, 5, 6, and something happens, as you can see. Now this oscillation here has changed from a wide oscillation to something narrow, while the thing here has become much weaker. This is 13.8 dBm, and I continue downwards. You can see the frequency of this thing here is changing. And you can see odd things coming up and going down. This is now 12.6 dBm. And I still have problems from the crystals. And this one stays longest, it seems. Here is something coming up and disappearing. And here is something. And it seems at this point all the problems from the crystals are gone. But that is only plus 5.5 dBm, far below the values I have been using before. So I have to do something, because I don't want these spurs or spurious things to be on the LO signal. Or I'm trying to get a perfect oscillator, and it shouldn't have noise sidebands or even sine wave-like sidebands. As it turns out, the voltage across the input crystals here is twice as large as the voltage across the second crystal. So I will put more crystals here to see if I can allow a little bit more power. I have doubled the number of crystals here. They are now 16, and I'm looking at the spectrum for crystal spurs and noise, and I'm at plus 15 dBm on the input with about 12 dBm on the output. That means 32 dBm on the box. So I stepped the power down in steps by half a dB. And frequencies change somewhere, and suddenly something stops and something starts. And I have seen ugly oscillations, but they don't come always. Well, here you have it. Well, I go back. And there are all sorts of ugly phenomena here, and they are fairly strong. So what I do is to insert 6 decibels of attenuation. And now I step, well, the problems I had here was at 12.5 dBm input. So I step upwards. $15.5, and I go down. And at this point, these fairly nice looking signals, they disappear at about 8.5 dBm. So I remove the attenuator again. And those signals are still very weak, but they are there. So I step down to see when they disappear. Six dB, something. And I go upwards. And here we have this ugly, unacceptable noise from crystals. And I put the attenuator back. And then those problems are gone. So I have crystal noise from the test system. So I will try to do something about that. Having noise both from the signal source and from the test system is confusing and makes it difficult to understand what is going on. But you see this pattern of coming and going spurs on the LO, on the sidebands of the LO. I have inserted an attenuator between this oscillator, which is now running as an amplifier, and the analyzing system. And this is what I see on the screen. Something is very wrong. So I try to replace this cable. And as you can see, that helps. So something is wrong with the cable. I have tightened the nuts of both B and C connectors very hard and put the bad cable back. And now it's okay. I don't see that interference anymore, but I do see the problems of crystal oscillations. So I turn in attenuation, 1 dB, 2 dB, 3 dB. And here we have some bad problem, 4 dB, 5 dB. So it seems the analyzing system needs to tolerate about 6 decibels more power than it actually does. Or I could try to do analysis with a 6 dB attenuator, but then I don't know the noise from the attenuator. This is the notch filter of the test system. Actually, it's 2 notches in parallel, each one with its own tuning capacitor. If I want this to tolerate 6 decibels more, means twice as much current, means twice as many crystals. That's a lot of crystals. Now there are twice as many crystals in this notch filter. Hopefully this will improve a little. This oscillator has now been running for several hours. The noise floor I see on the Leanrad screen is 2.26 dBm. Actually it is dB because the reference is not 0 dBm. The spectrum analyzer has also been running for several hours and it shows 9.32 dBm. I have connected the output now to this oscilloscope, which is a far more accurate instrument than the spectrum analyzer. And I see a peak-to-peak voltage of 17.6 volts. And here is another oscilloscope, and it shows, well, 17.8. Or 17.7. So, let's say, oh, and the oscilloscope is defective. It runs only for a couple of seconds and then it shuts off. But the calibration on that instrument is still okay. To get the same noise floor from the noise head, I had 2.257. Now it's 2.28. Well, the current through the noise head drifts a little with time when it gets warm. So something like 7.4 dB is the noise temperature I have to set on the noise head. With the noise figure meter on 9 dB, the noise floor I see is 3 dB above the room temperature resistor, which we have here at 0.03. I have added one more amplifier in front of the perceives, and that has reduced the noise figure. You can see here I have the 3 dB difference, and then I read 7 dB on the noise figure meter. The oscillator has been switched off for quite some time, and now it's cold, means it is room temperature at 24 degrees. And I switch it on. And as it happens, the noise floor is 3 dB above the system noise, which is the same as I had when setting the noise figure meter on 7 dB. But the noise figure is increasing. Sorry, the noise floor is increasing because the unit is getting warmer. And I have crystal problems. Now this time I think they are from the notch filter. I will turn the knobs on the notch filter and see if I can do something about this. Yeah, here it's much stronger. There are two notches in parallel and they interact a little, and the optimum tuning for minimum crystal noise is a little bit difficult. And you can see here there are these noise bands that are associated with these spurs from the crystals. But the general trend is it has gone from 3 dB to 3.2 now, and the temperature hasn't risen yet. Well, 2 degrees. We will see. The power level I see from the cold unit is plus 10.2 here, means plus 30.2 dBm. In this video I measured the power on the spectrum analyzer and the voltage on the oscilloscopes. And from that I can conclude that the power reading on the spectrum analyzer is too high by 0.4 dB. So it's very well within specifications, but still this is an error that I should remember for the future.